hypothesis testing with linear regression. So let's suppose we are interested in the relationship between family income and gift aid to students for a particular university or college. So the question is, are families with lower income receiving more or less gift aid? We don't really know because we haven't studied it, and we assume it is the case, but we didn't actually get the data to test that idea. And let's suppose we did get the data, and we plotted the data on a scatter plot, and we see we have family income here, so it goes up to the right, and then we see gift aid from university, gift aid from the universities to those students of those families. And clearly, it looks like this is what kind of relationship this is? Well, it seems linear and also negative. As one goes up, the other goes down. So it does seem at first that the more income a family has, the less gift aid they receive, which is supposedly a good thing because that's what the program was for. But as we have said before, it's not enough to just simply look at it informally or simply get an average and see if it is. We want to test the validity of this line, assuming those ideas of the normal distribution and how strong that line is, how confident we can be about that line in regards to in reference to the specific data points we have and the other ideas about normal distribution. So we can set up the hypothesis in the same way, and we would assume that the true linear model has a zero slope. This is the null hypothesis. So if a model has a zero slope, that means that there is no linear relationship between the two variables. And we can also set up an alternative hypothesis that no, the true linear model has a negative slope. In this case, we would assume that it has a negative slope. The theory indicates so, the data suggests so. So we don't need to just assume that it's different. We just have the alternative is that the true linear model has a negative slope. And then we set up the equation, the regression model. So gift aid is the outcome of response variable, the y variable. We have y-intercept. We don't need to set this up in the equation. The program will do that for us and make that inference for us. We need to identify the causal variable, or explanatory variable, and the error also is calculated by the program. So we don't need to worry about that, at least at this point. And then this here, this beta, is going to be inferred by the regression equation. And we can just jump right into the implementation in R. So we have here a gift variable. So we created this gift variable. So there's the vector or the list of all the gifts that have been given to the families. Oh, I'm sorry, no. This is just a variable we're going to place the results in, okay? Gift regression. So this is, for now, this is empty. So once the linear regression model runs, then it's going to be placed in here. So LM is the linear regression function, linear model, already provided in R. So gift aid, this is the gift aid variable. And then we use this tilde here, and then this is the Y variable, and this is the X variable. And this is the family income. And then we need to put a comma, and then there's another parameter for the linear model, which is the data itself. So usually this is just going to be the column name or the variable name. This is also just the variable name. And then we put the whole data set. In this case, it's called Elmhurst. And then close parentheses. And that's the end. And the basic information we need for a basic linear regression with one only causal explanatory factor. And then once we run this linear model, we need to run the summary function with all the results going to here, and then we run the summary function to get the output of all of that linear model that we ran. So this is all the results of it. There's a lot of information here. I want to focus on this part over here. Okay, this is the main results here. The coefficient. The coefficient is the beta, that slope of the line. So first, we have the intercept. So the intercept is obtained by that linear model, and here's 24. So when family income is 0, we estimate that gift aid is $24. So if family income is 0, gift is 24. That's the whole idea of the y-intercept. So there's a standard error for that value. There's also a t-value. So we're going back and using the t-distribution here to make this assessment. And then this is the p-value, the probability value. And when you start seeing scientific notation like this means it's a really, really small number. And here it indicates, because there's a code, significant codes, 003 stars means it's 0, 2 stars means it's 001 or less. Yes, I'm pretty sure, but I guess it's usually 1 star. It's not kind of clear here. 1 star is 0.5, 2 stars is 0.01, and 3 stars is 0.001 or below, 2 stars 0.01 or below, and 1 star 0.05 or below for the probability value. Remember, we want a very low p-value to make sure something is significant. If it's not less than 0.05, we do not consider it significant. So three stars here means it's really low. It's either 0 or below 0.001. So nothing is really 0 usually. So it's definitely below 0.001. That's for the intercept. Now let's take a look at the family income, which is the main thing we're interested in. So the estimate, this is the slope, which is the B, which is the impact of an additional unit of family income on gift aid, on the outcome variable. So here's negative. So if it's negative, we already see that the impact is negative. That is, the higher the family income, the less that outcome variable of interest, the y variable, in this, the gift aid in this case. So this negative already implies that we have a negative relationship. And then here's the actual value, 0.0431. So if we were to put it in that equation, it would be y, that is gift aid, equals 24.3 plus negative 0.043 times what? Times X, which is family income. So y is gift aid, and that's family income. So we identified the equation of the regression equation here. So the slope is negative 0.043. So every unit change in X will remove 0.043 in Y. And then we'll also get a standard error for that estimate value. We get a t value, and then we also get a probability value. And this is 0.00023, which is way below 0.001, which means it's significant. It's statistically significant. So we can accept that value. We can accept that family income is statistically different than 0. So we can't accept that the true linear model has a negative linear slope, that the slope is less than 0. It's not equal to 0. And we're making this determination based on the p-value. And that the estimate is negative 0.0431 with the standard error 0.01. Now, there's other information here about the what we call the adjusted R-square or F statistics, which helps us understand how much the model can actually explain the variation on the data. But we may only get into this later in the semester or in a more advanced course. So that's the main idea about linear regression in R. And it's very a good way to set up our hypotheses when we can clearly see that, or when we have the notion that, or the idea or the hypothesis that one variable like family income is going to cause or impact another variable. And the linear regression becomes even more important when we're talking about multiple linear regression, because we can include actually multiple factors, not just family income. Now we can start adding, well, what about race or gender of the person? Does that impact gift aid? Do people with certain gender or certain race get more or less gift aid? Do people who have better grades or worse grades get more gift aid, and so on? And we will examine that later.